Hey everyone, welcome back to the Systems Podcast, the show where we break down the systems behind modern software, startups, AI, infrastructure, and engineering at scale. Whether you're a software engineer, founder, student, or just someone obsessed with how complex systems work, you're in the right place. Let's get into it. So if you are listening to this right now, I want you to think about the very last time you bought something online. Just, consider the sheer scale of the engineering architecture sitting on the other side of your screen.
Oh, yeah, it's massive.
Right, you've got like exabytes of data, millions of sellers, these huge global distribution networks, and yet the only way you actually communicate with that incomprehensibly massive system is through this tiny blank white search box.
Which is pretty wild when you frame it like that.
It really is. And today we're doing a deep dive into a research paper from Amazon Search that details their query attribute recommendation system. And the core of this paper essentially admits that the absolute biggest bottleneck in e-commerce infrastructure, it isn't server latency or, database indexing. It's basically human laziness.
Yeah, it's like the ultimate UX bottleneck, right? Because search engines are, well, they're computationally phenomenal, but they're completely starved of input.
Totally starved.
The researchers actually call this an information shortage. When you look at their telemetry data, the average customer query on a massive platform like that is shockingly brief. The median length is literally just 3 or 4 words.
That is just wild to visualize. I always like to think of it like an analogy. Imagine you walk into this physical warehouse that holds, I don't know, hundreds of millions of items, and you walk right up to the clerk at the front desk, and you just grunt, "Red shoes."
Right, just 2 words.
Yeah, just red shoes. You don't mention your foot size. You don't say if you're running a marathon or like attending a wedding. You don't mention a budget, the material you want, just red shoes.
Yeah.
And you fully expect that poor clerk to walk into the abyss of this warehouse and come back in milliseconds with the exact perfect pair.
Which, mathematically speaking, is an impossible task if you're only relying on exact keyword matching. To actually rank products or source relevant ads or recommend good alternatives, the search engine's underlying algorithms, they need structured attributes.
Right. They need the details.
Exactly. They need defined variables for things like color, product type, brand, material. So when you only give them 3 words, you are essentially withholding the very parameters that the ranking functions need to even operate.
So, okay, if you're an engineer and you're looking at this information shortage, I feel like the intuitive solution seems kind of obvious, right? If a user types red shoes, why not just pipe that through some external knowledge base, like hook the search engine up to a massive LLM or Wikipedia or, I don't know, linguistic database like WordNet.
Sure.
Then the system looks up shoe, reads that it's footwear, and just expands the query automatically. Why doesn't that work?
Well, it's funny you mentioned that because that was actually the industry standard approach for a long time. Engineers definitely tried to bridge that gap by integrating general knowledge graphs to, expand those really sparse queries.
Okay, so it has been tried.
Oh, absolutely. But the paper points out that those attempts hit this hard scalability and relevance ceiling. And the main problem is domain context. Like, Wikipedia is a general encyclopedia. It knows the historical origin of the shoe, maybe, but it doesn't possess structured, specialized e-commerce relational data.
Oh, I see what you mean.
Yeah, it doesn't intuitively know how a specific brand of red shoe mathematically relates to, say, the current seasonal catalog of athletic wear in one specific geographic market.
Right. Because in a general knowledge graph, the word apple might strongly associate with, like pie or orchard. But in a product search engine, if you type apple, the system needs to completely ignore fruit and just immediately associate it with laptop or phone or charger.
Exactly. Generic dictionaries just do not help you map consumer behavior. And that domain gap is exactly why Amazon Search realized they really had to build a custom system. They needed an architecture that could essentially read between the lines of those 3 or 4 words, but using deep proprietary product context.
Using their own massive data.
Right. The researchers frame this as a transition. They're moving from relying purely on explicit attributes to generating what they call implicit attributes.
Okay, this is where the engineering gets super interesting to me.
Hmm.
Let's ground this in the paper's primary example just so we can follow along. Let's say a user sits down and types just 2 words into the search bar iPhone 8.
Okay, so if we isolate just the explicit data there, what do we actually have? We have a string of characters. A naive parser might look at that and identify iPhone as a model and 8 as a version number. And that is pretty much the absolute limit of the explicit information provided.
Yeah, there's not a lot to go on.
No, it's really not. And if the backend only matches against those explicit tokens, your recall pool is going to be incredibly narrow.
But the query attribute recommendation system they built, it takes that tiny string and essentially performs like computational telepathy.
It really does feel like that.
It outputs this comprehensive list of implicit attributes that the user just never typed. It infers that the brand is Apple. It infers the operating system is iOS. And then, this is the crazy part, it goes a step further and crosses into behavioral predictions.
Yeah, this is the breakthrough.
It tags phone case as a complement to the query, and it tags Samsung as a substitute brand.
Yes. The inclusion of complement and substitute that is the critical breakthrough of this whole architecture. It isn't just mapping a static product taxonomy anymore. It is dynamically mapping the actual consumer ecosystem around the query.
Okay, but I have to push back here a little bit, or at least, play devil's advocate for anyone listening. Figuring out that an iPhone is an Apple product, that feels trivial, right? That's just a basic relational database lookup.
Sure.
But behavioral nuance, how does a machine discern that a Samsung is a substitute that you might want instead, while a case is a complement that you might want with it? Strictly from the screen iPhone 8. Like, how does it extract behavioral relationships from two static words without just hard-coding millions of if-then rules?
Well, that is the core engineering challenge of the whole paper, because you're right, you absolutely cannot hard code it. At Amazon scale, trying to maintain a manual rulebook for hundreds of millions of product relations is just impossible.
Right, it would be a nightmare.
A total nightmare. So instead, they built a highly structured pipeline that calculates these relationships mathematically, and it happens in 3 distinct phases: intent classification, explicit attribute parsing, and finally, implicit attribute recommendation.
Okay, let's avoid just walking through this like a boring table of contents and actually dig into the mechanisms. To figure out the behavioral graph, the system first needs to know what universe it's operating in, right? So phase 1, query intent classification. This is basically the machine predicting the broad category of the request. Like if I type Nike shoes, it needs to classify the intent simply as shoe.
Exactly. The paper defines query intent very specifically as the product type. So Amazon maintains this internal ontology, this strict hierarchical mapping of between 2,000 to 3,000 distinct product types. The first model's job is just a massive multi-label classification task.
Got it.
It says, given a short text query and the user's country, which of those 3,000 product types are mathematically probable?
And doing this at a global scale just introduces this brutal layer of complexity, because a string of characters in the U.S. might have a completely different intent than the exact same string in, say, Germany.
Oh, 100%.
How do you even train a model to understand 3,000 intents across dozens of languages without injecting massive human bias?
You use the users themselves. They trained this classification model using 1 full year of historical search logs. They just aggregated the query, the marketplace, and the exact product types that users actually clicked on or purchased after making that specific query.
Oh, wow. So they just watched what people actually did.
Yeah, it's this incredibly elegant application of automatic labeling at a massive scale. No humans were in the loop sitting there deciding what a query meant. The model simply learned the probabilistic distribution of actual human behavior.
That makes a lot of sense.
Yeah.
If millions of users type iPhone 8 and overwhelmingly click on products tagged as mobile phone, the system just naturally weights that intent. But let's look under the hood of the model itself for a second. The paper states they use a BERT transformer architecture for this intent classification.
Me too, yeah.
If I understand transformers correctly, they're designed to look at the entire sequence of tokens bidirectionally to grasp context, right?
Right, they look at everything at once.
But how do you get a single unified intent prediction out of a sequence of multiple varying tokens? Like, how does it boil it down?
Okay, so that requires looking at a very specific mechanism within the BERT architecture, which is the CLS token or the classification token.
Okay.
When you feed query into BERT, it generates dense vector embeddings for every single word. But the CLS token, it's actually prepended to the very start of the sequence.
It's like a dummy word at the beginning.
Essentially, yeah. And as the transformer's self-attention layers process the text, this special token acts as a sort of aggregation node. It uses attention weights to literally pull contextual information from every other word in the sequence into its own vector. So by the time you reach the final layer, the embedding of that single CLS token mathematically summarizes the entire intent of the whole query.
Oh, that's really clever.
Right. And then they just pass that one single vector through a linear layer to predict probabilities across all 3,000 product types.
That makes perfect sense. It basically acts as an information sink for the whole sentence. But if you're listening and wondering how this doesn't just completely collapse when you introduce the global variable writing leave, like say a specific brand of shoe exists in the UK, but it absolutely does not exist in the Japanese catalog, does the system have to load 20 different massive BERT models for 20 different countries?
No, because loading separate massive language models for every marketplace would be computationally disastrous. The latency would be awful.
Right.
Instead, they use this remarkably efficient trick, a country ID physical mask layer, so they concatenate all possible global labels into one massive output space. But during inference, the system takes the user's country ID and physically masks out the logits, the raw predictions for any product types that don't exist in that specific market.
Oh, wow. So it just zero outs the impossible options.
Exactly. It forces the model's probabilities to zero for irrelevant local items, which lets them use one single unified model to serve global traffic accurately.
That is just a phenomenal way to save compute while keeping the architecture unified. Okay, so the first phase grounds the query in a broad universe we know it's a phone. The next phase is explicit attribute parsing. This is about actually tagging the individual words, right? If I type red Nike shoes, the parser goes in and tags red as color, Nike as brand, and shoes as product type.
Right. So while the intent model looks at the holistic meaning, the parsing model operates at the token level. It's assigning semantic meaning to every single word. And they utilize another multilingual transformer for this just to ensure it can handle diverse grammatical structures. Like whether the adjective comes before the noun in English or after it in Spanish, the transformer can handle it.
But the data gathering strategy here is a total pivot from the first phase. For the broad intent, you said they just ingested a year of passive click logs. But for this explicit parsing, the paper notes they had humans manually hand-label over 600,000 queries across 12 different languages.
Yeah.
Why the massive shift? Why rely on passive clicks for one thing, but invest massive capital into manual human labeling for the other?
It basically comes down to the fundamental nature of the machine learning task itself. Broad intent is highly correlated with user behavior, right? Clicks are a near-perfect proxy for what someone meant broadly.
Yeah, that makes sense.
But token-level parsing requires strict linguistic ground truth. You really cannot reliably deduce from just a click whether the word red modifies the primary product or maybe it modifies a secondary accessory in the image.
Oh, I see. A click doesn't explain the grammar.
Exactly.
Yeah.
You need human judgment to explicitly map those text boundaries and assign semantic attribute categories, especially across highly variable global languages.
Okay, so we've mapped the explicit data. The pipeline knows the text says iPhone and it knows the broad intent is mobile phone. But we still haven't solved the core mystery here. How do we get from these explicit tags to actually understanding that Samsung is a substitute and a case is a complement?
Right, the real magic.
That brings us to the centerpiece of the whole architecture, the attribute relation graph. To predict implicit attributes, the system basically has to construct a map of how every attribute in the world relates to every other attribute.
Okay.
And it builds this map utilizing two massive data pipelines.
The first one being the internal product catalog data, right?
Yes.
The raw information uploaded by the sellers themselves, brand names, specs, materials. Though I noted the paper mentions Amazon actually has to run automatic anomaly detection on this data because sellers notoriously keyword stuff or, intentionally mislabel their products to get views.
Oh yeah, quality control on the catalog side is vital. It's a constant battle. So you take that cleansed catalog data and you merge it with the second data source, which is the parsed query data we literally just discussed. So now you have a dual-sided view. You know how attributes relate within the physical products themselves, and you know how they co-occur when users actually search for them. But wait, if you're an engineer listening to this, alarm bells have to be going off right now regarding time complexity. If you are trying to cross-reference thousands of unique attributes against hundreds of millions of daily queries, creating edges between every single node, that is an n-squared scaling nightmare. You cannot traverse a graph of that magnitude in real time when a user hits enter.
You're entirely correct. The computational cost of a monolithic graph like that would just grind their servers to an absolute halt. The engineering solution here actually loops back to the very first phase we discussed, the product intent.
Oh, okay.
They recognize that attributes across different product types almost never intersect mathematically. Like, the attribute operating system will heavily co-occur with phones and laptops, but it will literally never co-occur with running shoes or garden hoses.
Oh, I love that. So they basically shatter the monolithic graph. They
Yeah,
partition it based on the intent.
exactly. They partition it into computationally manageable subgraphs, and once they have these intent-specific subgraphs, they apply graph neural networks, or GNNs, to generate embeddings for every single attribute node.
Okay. Let's make sure the mechanics of a GNN are crystal clear for everyone. Because I've used standard feed-forward networks, but a GNN operates quite differently. How does it actually extract, substitute, or complement from a partitioned graph?
Yeah, it's a bit different. A standard neural network typically looks at a data point in isolation, right? But a GNN operates on the principle of message passing.
Message passing, okay.
In a GNN, an attribute node updates its mathematical representation by aggregating information from all of its neighboring nodes. Over multiple layers, a node gathers context from its immediate neighbors, and then its neighbors' neighbors, and so on.
Let me try a visual analogy for this, because I think it helps. A lot of people, myself included, usually imagine a graph as like static sticky notes connected by string on a whiteboard.
Right, the classic detective board.
Exactly.
Yeah.
But based on what you're saying about message passing, it's actually more like a complex network of plumbing. Like water flows from the iPhone node to the Apple node and the phone case node, carrying data with it. And the edge weights, basically the thickness of those pipes, are determined by how often those attributes co-occur in the click logs in the catalog.
Yes.
So if users constantly buy cases with iPhones, the pipe between them gets super wide. A GNN isn't just looking at the static connections, it's capturing the actual volume and direction of the traffic flowing through that specific neighborhood.
That pipe analogy is highly accurate. I really like that. Through that message passing, the GNN translates the topology of that plumbing network into dense mathematical vectors, which we call embeddings.
Right.
Nodes that share similar topological neighborhoods end up mathematically close to each other in vector space.
Yeah.
So iPhone and Apple will point in almost identical directions. But Samsung will be positioned in a specific mathematical relation that the network recognizes as a substitute.
Because it shares similar catalog structures, but rarely co-occurs in the exact same cart purchase, right?
Exactly. Whereas a complement, like a case, shares a completely different topological pattern entirely.
Man, that is so cool. So they've built this beautifully optimized, mathematically weighted plumbing network. The GNN has mapped the exact relationships.
Yeah.
But, training a model offline is one thing. Deploying it for online inference is a whole other beast.
Oh, for sure.
When I'm sitting on my couch and I hit search, the system has to return results in a fraction of a second. It does not have time to reevaluate the entire graph.
No, it doesn't. And that brings us to the real-time execution step. When your query hits the server, the system instantly grabs the explicit attributes from the parser and the broad intent from the classifier. It uses those to drop into the correct subgraph, so the correct room of plumbing in your analogy.
Right, the tech room, not the shoe room.
Exactly. And from those starting nodes, it executes what researchers call a graph random walk.
Okay, if I'm designing a deterministic search engine for a massive retailer, the phrase random walk sounds kind of terrifying. You don't want randomness when a customer is trying to buy something.
I know it sounds bad, but it's a stochastic mathematical term. In this application, it is heavily biased, not purely random at all. Imagine injecting a tracer die into your plumbing analogy at the iPhone node. The system simulates taking thousands of rapid steps through the graph. And at every single intersection, the probability of taking a specific path is dictated by the edge weights, the thickness of the pipes.
Ah, okay, so it's a probability-weighted traversal. It's much more likely to flow down the massive pipe toward iOS than to, trickle down some tiny, obscure pipe.
Precisely. By rapidly simulating these weighted paths, the system quickly aggregates a distribution of the most frequently visited neighboring nodes. The nodes that accumulate the highest visit counts during this little microsecond simulation, those become the recommended implicit attributes. And because the graph is pre-partitioned by intent and the embeddings are already pre-computed by the GNN offline, simulating this biased random walk literally takes milliseconds.
That is genuinely incredible. It takes a three-word grunt, grounds it in intent, parses the grammar, drops it into a dynamically weighted behavioral graph, and then simulates thousands of traversal paths in milliseconds to basically read your mind.
It's pretty amazing.
But let's bring this back down to earth for the listener for a second. What does this invisible heavy lifting actually achieve in production? How does this impact the real-world metrics when Amazon actually deployed it?
The paper outlines three massive areas of impact across the platform. The first is product ranking. Remember, ranking functions are deep learning models that require rich feature vectors to score products. When you feed the ranking model these new rich implicit attributes, it gains a multidimensional understanding of the shopper's true intent. It stops just blindly matching the keyword iPhone and starts matching the underlying requirements.
Right. So if the graph explicitly tells the ranking model that my implicit intent requires iOS, the system will aggressively penalize some cheap Android knockoff that happens to have the word iPhone stuffed into its seller title.
Exactly. It filters out the noise because it actually understands the boundaries of the request.
That's huge. What's the second area?
The second deployment area is product ads sourcing. Advertising systems rely on the search architecture to determine which sponsored products are actually relevant to show. By generating implicit attributes, the system vastly expands the pool of eligible, highly targeted ads. It doesn't just show you ads from companies that explicitly bid on the exact string iPhone 8.
Oh, I see.
It understands the graph topography well enough to show you an ad for, say, a premium OtterBox case, because it recognizes it as a highly relevant complement to your explicit search.
So it serves ads that actually align with the peripheral shopping journey rather than just blindly matching text strings. That's a huge revenue driver, I'm sure.
Oh, absolutely. And the final area of impact? Query rewrite.
Query rewrite.
Yeah, this is basically the invisible safety net for user error. Customers constantly write clunky, misspelled, or just overly broad queries. The implicit attributes provide the search engine with the structured data required to silently reformulate that clunky query on the back end. It essentially rewrites your input into a highly precise search string that perfectly maps to the catalog's architecture before it even hits the retrieval phase.
If you're listening to this and wondering why this matters beyond just theoretical computer science, this is exactly why modern e-commerce feels seamless. When you type 3 lazy words into a search bar and the exact right product, a perfectly complementary ad, and a valid substitute alternative all render instantly on your screen, you aren't just querying a database. You are reaping the benefits of a multilingual transformer, a year of global click data, graph neural network embeddings, and real-time probability-weighted random walks.
Yeah, it's really a masterclass in using complex machine learning systems to bridge the structural gap between flawed human communication and rigid database logic. The pure engineering effort required just to compensate for the fact that we don't want to type a full descriptive sentence is staggering.
It is staggering. It really makes you rethink the little white search box entirely. But it also raises a deeper question, something I kind of want to leave you all with mull over. If a distributed system can perfectly map out our implicit desires based on just 3 words, if it can mathematically infer our substitutes and our complements based on billions of graph edges, land bait, are we just searching for products, or are these attribute graphs beginning to map the very architecture of human consumer logic? If a graph neural network knows what we consider a substitute better than our own conscious brains do, who is actually guiding the shopping trip?
That is the philosophical edge of behavioral engineering, a really fascinating space to watch.
That wraps up today's episode of the Systems Podcast. If you enjoyed this episode, make sure to follow the podcast, leave a rating, and share it with another engineer or tech enthusiast. And remember, great products are built on great systems. We'll see you on the next one.